Hi everyone, my name's Alex Kingsbury. I'm going to talk to you today about wire and arc additive manufacturing, give you a bit of a global overview, and then also talk about some of the latest developments. Whenever we talk about any additive technology, I feel it's always best to talk about the standards first. So just understanding where does that additive technology fit within the seven designated categories of additive manufacturing. So wire and arc additive manufacturing actually sits within directed energy deposition. It's got a pretty vague description where it's basically saying we're putting material into an energy source, but really we have two different types of DED. It's also known as DED. Powder-based DED and wire-based DED. So powder, we're throwing powder into our energy source. Wire, we're putting wire into our energy source. WAAM is a subset of the wire DED. So with wire DED, we can have a wire plus an electron beam. We can have a wire plus a laser. These are different types of DED for wire. But when we talk about WAAM, the key differentiator here is that we are forming an arc between our wire or an electrode and the workpiece. So it's the arc that is the energy source. We have three, broadly speaking, different types of WAAM, wire DEDs. So gas metal arc welding, gas tungsten arc welding, and plasma arc welding. Gas metal arc welding is a MIG-MAG based process. So this is welding type process. It's the most common, and it's where you form an arc between the wire here and the workpiece. Whereas gas tungsten arc welding was where you have a tungsten electrode that establishes the arc, which you can see in the middle here, and then you feed the wire into that arc and it melts and forms a deposit. Gas tungsten arc welding has been used for welding just to join pieces together. But in the case of WAAM, where we want to use it for 3D printing, we do have to put a filler wire in there. Plasma arc welding is similar in that it also uses a tungsten electrode to establish that arc, but we also are feeding a highly ionized, very high temperature gas as well. So it's a very high energy density process. It's a higher energy density process than gas tungsten arc welding, but not quite as high as laser welding. If that makes sense. It's got a narrow weld beam, and that means you can do some, very thin walls, and it has a less heat affected zone area as well. So it's quite good with reducing distortion. The gas tungsten arc welding and plasma arc welding, like I said, they both need that filler wire, and that's a real differentiator between them and the gas metal arc welding, where you are using your wire as your electrode. There's advantages and disadvantages to this. So using a filler wire, you can vary your feed speed with the current. So with the gas tungsten arc welding, plasma arc welding, we're able to independently vary the current and the wire feed speed. So that gives us a lot more process flexibility than gas metal arc welding has. However, having to use a filler wire means you do need to make decisions around how am I going to feed my wire? What angle am I going to feed it in? Am I going to feed it on the leading edge or the trailing edge? And it can create some difficulties around process path planning and, doing things like sharp turns and so on. But, it really it's horses for courses, and you tend to use the one that's most suitable for your material. A typical setup I've got just depicted here. So we start with our, we'll have some sort of a power source here. We have our welding torch there. We have something manipulating that power torch. We have our product being built up here. Thin wall it's got. So typically WAAM structures are thin walled structures, and I'll talk a little bit about that in a sec. We build our structures on a substrate, which is typically clamped to our platform. We always have an inert gas connected. A shielding gas is very most commonly used. It's very economic to use a shielding gas. And if this is the plasma process, we'd also have a plasma gas attached to that as well. One thing here that's worth mentioning is that you can also have a turntable. So, this table down here, platform, can be manipulated as well. And the other thing too is this, whatever's holding your weld torch, it can really be whatever you want it to be. So typically it's a robot, or it could also be a gantry. With the combination of that plus a shielding gas, what that means is that you have a lot of flexibility and a lot of space in which to use. So you can build as far as your robot can swing. You can build as far as your gantry wants to go, essentially. So it's quite good for medium and large type parts. And also you don't need support structures typically if particularly if you're able to do a turntable in combination with a robot. So you can have a lot of good flexibility with the WAAM system. Some of the advantages of wire and arc AM, and there are heaps, and I won't labour the point too much, but I do want to cover off on what are some of the real highlights. So for starters, wire and arc additive manufacturing, as I've just described, those three types of welding technologies, they're welding technologies. So they've been around before WAAM, they've been around before 3D printing. So we have a whole lot of decades worth of experience and knowledge. All the guidebooks have been written, all the handbooks, and all of that welding know-how, we can bring that into WAAM. It's a huge advantage. It's a very high deposition rate technology. So we're talking kilograms per hour, not grams per hour. Material utilization is really high. So we would typically look to have at least 90% of our product that we buy in is used in the final product, if not more. Our lead time, because there's no tooling required, is very low. And also it's, as I've said, very good for medium to large scale parts. It's a very cost-effective process, and that's why it's very attractive to industry, because there's low capital costs and low running costs associated with WAAM. One of the really great things though about WAAM is the fact that it's a wire-based process. So we're not using powder, which has some storage and handling issues, some process issues with powder. Wire is very straightforward. It has established supply chains. So the wire that you use with WAAM is exactly the same as all of the welding wire that you would just buy off the shelf. And really that translates very easily. And likewise, we're working with known alloys. So a lot of people who are in industry looking to use WAAM can do so very simply, crossing over if they're able to use like-for-like alloys. The certification process is generally a bit more streamlined because we're using certified alloys in this process. And the changeover time is really simple. You just start your next wire up and you're off and away using another alloy. So a very simple process really, and very robust. There's a number of different commercial players around the world. I've got them listed here. There's plenty of others as well that would operate sort of smaller bureau type activities. But these are some of the main suppliers out there in the market. Often they're selling machines, selling equipment, selling turnkey packages. So when I described that system before, of course, you can buy all of those things off the shelf and put them together yourself if you want to. But these are suppliers that will sell you really like a turnkey system. So much more sort of user friendly. Some of these suppliers also sell software. Some of them got into selling the power source first. So they're welding suppliers and now they're offering turnkey systems. Some offer bureau services as well, and some even offer design and consult services. So there's quite a number popping up, and definitely over the last few years, there's been quite an explosion in these providers. The commercial landscape for WAAM is quite interesting. So there aren't many industries that, engineering sort of typical industries that wouldn't use WAAM for some reason or another. I've got all of the sectors listed there, and there could be others as well. But really all of those have been known to use WAAM products and to start going down the certification pathway to use it more, probably more importantly. WAAM products tend to be really good for disrupting casting and forging supply chains. So casting, absolutely, it's sort of almost a gimme for replacing castings, particularly when they're long lead time items or they might be low volume items. But forging as well, which is really interesting because you can actually get equivalent properties or better from WAAM than from forging, which is very promising. Some common alloys that are used commercially are titanium, nickel-based superalloys, aluminium, steels. They tend to be high-value materials. So you have that sort of generally like typical AM value prop that's going on for laser powder bed fusion as it does for WAAM as well. High butterfly components, so your aluminium, wing ribs where you'd have to do loads of machining. Instead, you could just have a forged plate and then build up a rib structure around that much more cost effectively and quickly. And great for, lead time sensitive parts. Just to give you an idea of commercial application, I think this is a really good one. So this is a part made by AML 3D in Adelaide. They made that for the Keppel Corporation. They have a whole division around ship repairs and supplying parts. And they wanted this part made. It's called a Panama chock. And for those of you that aren't in the shipping industry, what that is a guide for a mooring line that would sit on the end of a boat. But it's a very big part. It's typically cast and it has a very long lead time, which is kind of a bit of annoying for Keppel. So what AML was able to do is to make this as a thin-walled structure. And as a result was able to reduce the weight by 30%, which for shipping is a really big deal. The product itself, the final product from AML, ended up being twice the strength of the casting, which is significant. So really, you probably could have reduced the weight even more. And the lead time was reduced for this part as well, like 6 months, being able to take it down to a month. And there was cost savings connected with it as well. So who's not happy about cost savings? So all in all, a really good example of where you can make WAAM really work well. Now, having sold you on all of the wonderful things about WAAM, there are still some challenges, definitely, or some pain points that we have and we have to contend with WAAM. Now, I just have talked about how welding has been really great. We've been able to use that and transfer that over to WAAM, but not quite as simple as that, unfortunately. So what we have is when we start building our first layer, that's a lot like welding, and that weld beam will behave much like a typical weld would. And we have a lot of, heat transferring into this substrate, no issues. Now, as you start to build up your structure, your heat transfer changes. And what this means is that you end up with a lot of heat accumulating in the part itself because we don't have a nice big substrate to transfer heat to. We've just got the structure underneath to transfer heat to and the surrounding air, which, as we know, heat transfer to air isn't that effective. So we get heat accumulating in the part gets quite hot. As you keep going up and up and up, you tend to get this, you get a repeated application of a thermal source. And so this, if you take, for example, this one part here of the part, this is going to be subjected to a number of different applications of heat. This can be pretty problematic when it comes to your microstructure. You can get some columnar grain growth. It's very common with WAAM. And columnar grain growth tends to lead to a reduction, in general reduction of properties, and tends to lead to anisotropy. So we get, we're less strong in this direction than we are in this direction, which leads to a bit of part performance variability, which is really not a good thing if we're talking commercial applications, and we need to know that the part is strong in all directions and strong, to a certain degree, and can do that repeatedly and consistently. So we don't really want columnar grain growth. Porosity can also be an issue when you have a slightly unstable weld, which is common, and our weld profile variability. So we can get, if we've got a bit of heat transfer change. So for example, if you have like a cross section, the heat transfer is going to change. So the weld will flatten, and then in that bit, you get a little bit of a dip. And then you might go along. So this dip then leads to, and I've got here what I've termed the princess and the pea phenomenon, because if you have one issue down here, that issue just repeats and repeats and repeats and becomes more and more of an issue the further up you go, which can lead to dimensional intolerance or inaccuracy. And also, I guess, best case scenario is just you're doing a heck of a lot of machining to try and get off the excess, which is annoying and not very cost effective. We also have some residual stress and distortion that happens. The surface finish is a little bit wavy, not great to look at, but probably more importantly, this is, a wavy surface can be an initiator of cracks. So we can get our cracks initiating in that wavy surface. So you typically like to go through and just do a little finish machine and machine off the wavy surface. So to address all of these challenges, of course, we have R&D, and there are a lot of really great institutions all around the world working on wire and arc additive manufacturing and looking at a number of different areas. At RMIT, we are doing work in wire and arc additive manufacturing across a couple of different areas of the university, actually. And we're spreading ourselves across these 5 areas that I've highlighted. So that's one thing I'm very excited to talk to you about today. We have wire and arc systems set up in our architecture and design school, actually. So we have some really great architects and designers in the School of Architecture and Design. And can I tell you, there is no greater challenge to an engineer than working with an architect who wants to create the most incredible and amazing structures. So, you know, this team have really pushed the envelope in what this technology is capable of in terms of form, function, and what they're finding is they're really testing the robustness of this process. Our School of Architecture and Design is doing a really great project with a company called Urban Art Projects in Queensland and QUT. And one of the things they're finding is that they'd really like to, or one of the things they're working on is developing a sensing and feedback system. So, you know, this is where you have that, like I was mentioning, that princess and the pea phenomenon happening, where you have to be able to self-correct. So it's really not enough to just deal with these inaccuracies. It leads to, you know, not only does it lead to a dimensional instability, but it also actually leads to some process instability. And that's where you start to get a lot of porosity happening, which is not a good thing. And it leads to just a structure that does not work. So these guys are looking at all types of architectural forms, anything from facades, but also structural pieces. They're working with steel at the moment, and we're going to be working on aluminium together, which is something I'm really excited about. So moving on, and so they're really looking at the process control. Moving on to materials, which is what I mentioned, aluminium. One of the things that we find with WAAM, as I've described, we've got that, you know, the characteristics of WAAM are not quite the same as welding. So what we find, and what we like to say about WAAM is, if you can weld it, you can WAAM it. If it's weldable, it's WAAMable. Well, actually, that's not entirely the case. So in fact, what we have found is that some unweldable alloys will actually work quite well with WAAM. And really what we need to do as researchers is look to really exploit the characteristics of WAAM and enable it to do, you know, materials that you couldn't ordinarily weld. One of the things I'm really interested in doing is looking at high performance aluminium alloys and working out how we can get those to work with a WAAM structure. So I think if we can do that, we can then open up loads of more applications for WAAM, because I think this would be really valuable. Modeling is something that we do at RMIT, and we've done extensively in additive manufacturing. And what we're going to be doing soon, we're working with an Austrian consortium of a auto supplier and research institute and a technology company. And we're going to be using all of our models that we've developed for microstructure, properties, performance, and crossing those over into WAAM and saying, okay, well, how do they work in a WAAM system? The cooling rates are very different in WAAM than what they are in like a laser powder bed fusion system. So we definitely need to readjust and edit our models. But if we can do that, we can start to do things like determine how can we get, how can we reduce that columnar grain growth? How can we reduce the crack propagation happening? How can we change our materials to stop that happening? Heat treatment is a kind of a very overlooked area for WAAM. So a lot of alloys will be heat treated once the structure is made. And we typically just use standard off-the-shelf heat treatment recipes. We really need to look at what else we can do on the heat treatment side of things. And thermal controls, this is a really kind of obvious one for WAAM, given the variance in the thermal history that we have in a part. We as, I think, engineers and scientists really need to do a better job of being able to more accurately control this thermal history of a WAAM-made product so that you get better microstructure, better properties, and better performance, and can do that, quite reliably and predictably. In summary, though, I think that WAAM is a really interesting area. It has sort of somewhat come from left field, but it has come with this wealth of knowledge from welding that we can really rely upon. And I think we can really build on that knowledge to make more WAAM-specific alloys. We can make more WAAM-specific models, WAAM-specific heat treatments, and I think that's going to really grow the application area. It already exists before we even kind of imagined it into existence in a way. So there's loads of applications out there that are just crying out for this, and a lot of opportunity. So look, in summary, thank you so much for listening. I did have a couple of references in there. Please contact me if you're interested in the reference list. And if there's anything I've said today that's piqued your interest, please reach out and get in touch. I'd love to hear from you. Thank you so much to Magda and the TCT group for inviting me to talk. It's been a real pleasure. I wish I could be there in person. I miss you all, and I can't wait to see you again. Thank you.